If they're in communicate, if they're texting you or something, which I do. Oh, here they are. Oh, sorry. Okay, thank you. Got it. Got it. Okay. 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 Oh God, totally. Okay. Okay, everybody, sorry about that. All right, so I was just babbling for like 5 minutes while people were out in the waiting room. My bad. In a way, and I was trying to sort of catch everybody up to say what we were doing now and why, what it was. And I'm sorry, but it was probably more than necessary. But also the recording just started too, for anybody who's not seeing this. So the point is I want to pick up from where we were last time with the constant acceleration equations. And I want to give another exercise for you guys to work on in class. And just be aware that just like last time, it may seem tricky, but the tricky part is the difference between acceleration and velocity. And by the way, if you ever struggle with acceleration and velocity, this is the real thing. I'm going to try to give it to everybody through English. I'm going to try to give it through equations. But where'd my board go? Sorry. I'm like, okay. I'm going to try to give it through equations and try to give it through English. But if ever you have a moment, ever, where you're trying to do any homework or work on any problem in class, or God forbid, working on an exam or something, which will not sneak up and surprise you. There's no exam this week or something like that. That's just going to happen out of nowhere. But if you were in the middle of anything stressful in physics, and for one moment, it occurred to you like, wait, I'm not totally sure of the difference between velocity and acceleration, or the relationship, or I'm not sure which equation means what or whatever. It's great to recognize if you have that moment and realize no matter how many times that you should not be ashamed, and you should ask me a question or turn to someone else or look up something in a book. If ever you're trying to get straight the difference between velocity and acceleration, it doesn't mean that you totally missed 3 classes and you missed the basics and it's too late to say that, or that you're crazy and missing something obvious that everybody else is getting. Most of physics really is about getting the subtle distinction between velocity and acceleration, like really feeling it. So whenever you recognize that you're not feeling it, you should actually totally ask or look for more on that, because that means you're on the right track of actually trying to get it straight. It's hard to get it's very easy to think that we have it straight before we really do. So anyway, on that note, back to the equations. These are the equations we have so far, like all of them. Or in fact, I'm going to say these are the useful. Well, anyway. Those 2 equations intentionally look very similar to each other. They're supposed to. Then now I'm sort of, you could say, writing them in. I don't want you to memorize that one equation is called equation 1 or something like that, but we also have. But please do rewrite these with me, even if you think you totally know them, or the more you can just write them without thinking about it, the more you'll never have to think about them again. Okay, and again, I said this last time, I'm going to say it again now. Equation, I don't care what you number them, or I always write them or try to write them in vaguely the same order, the order that we develop them. But just the key thing to notice is that equation 1 and 2 are useful, and you do actually directly write them down to start problems, and you do end up plugging into them. 3 and 4 are more about understanding and telling us things. They're more about insert math here. They don't directly do much for you on an exam or anything. But then finally, the last equation we have so far, but we're going to use it to make more equations today. The last one we have so far is this one, which that's the one that's the one in a way we're focusing the most on. That's the one that's the most slippery. It's not always true. It's only sometimes true. It's and it implies more things than just a plugin. But we talked about that last Wednesday. We'll see it more today, more examples. But these, as far as I'm concerned, these are the equations we have so far. Definition of average velocity, definition of average acceleration, definition of instantaneous velocity, definition of instantaneous acceleration, and then finally a consequence of average velocity, or a way of getting average velocity that only works, and this is the key, this is where we move on today, that only works right, if A equals A naught. Wait, that's supposed to be an IFF, if and only if. And A equals A naught is really the secret underlying condition of all the stuff we're doing right now in physics. That's a way of saying constant acceleration. Everything we're doing right now is assuming that you have some kind of value for A that lasts for more than one moment and that you can plug into equations and say things about. Now, so tell me if you want, so I'm going to the next page, but tell me if you want me to go back. Okay, the whole example from last time, whether it was a couple of parts to the exercise or one, the facts that I gave you were, imagine some object that starts from rest and accelerates from rest at a constant acceleration rate of positive 5 meters per second squared, right? And then I asked things like, where will it be after 1 second? Where will it be after 2 seconds, etc. And, you know, the big summary is it's very easy to think, in a situation like this, if these are the two facts you're given, if I say, where is this object after 1 second? It's a very common instinct to think, oh, it'll be 5 meters after 1 second, like distance equals rate times time. The real answer we found last time was no, it'll be 2.5 meters after 1 second, actually, because distance equals rate times time, meaning average rate of speed. And if you really look at the numbers of this, if you look at them in your head or you run equations, you could see that what this is really trying to say in English is that something that accelerates at a rate of 5 builds up speed from 0 to 5 in the first second. So on average, it's not going as fast as 5 any more reasonably than it's going as slow as 0. It's going in between 2.5. So it does that for a second, and that's the answer. Okay, that's what we saw last time. What I want to say now is you've had some labs. This situation of having an acceleration value, but having that value not change, is what we're supposed to have concluded from lab 3. Okay, lab 3 is a weird lab in itself. I mean, it's got easy parts, it's got hard parts, whatever. But the upshot of lab 3 is supposed to be that we're supposed to recognize, oh, this situation of a change that is not changing, a constant acceleration, actually is not only sort of, you know, reasonable to analyze mathematically, but really does occur in space and time, like in the very all-pervasive case of free fall. Like the point of lab 3 in a way is supposed to be to show that when things freely fall, when they are under the influence only of what we call gravity, whatever that is, that when things freely fall, they do have velocity and reliably, otherwise they wouldn't fall, they're moving, and they don't maintain a constant velocity, they do change their velocity. But apparently, at least when we're near the surface of the Earth, if we're at like reasonable heights, like below like even as high buildings, but not much higher, then things gain velocity while they fall, but at a non-gaining way, in a non-gaining way. In principle, all the stuff you do with the bolts and everything in lab 3, you're supposed to be showing yourself, we're supposed to be verifying to ourselves, not anything about numbers, but just about patterns. We're verifying to ourselves in lab 3 that free fall is a naturally occurring and very, very common case of constant acceleration. In other words, a case where these equations and stuff apply. And it's not supposed to be a trick. I mean, we do believe that. It's not perfectly true, but it's approximately true. So let me make it clear. Okay. Sorry. First, let me say, to be clear, I'm going to use the term free fall a lot. We use the term free fall a lot in physics. In principle, you analyzed it or explored free fall to some extent, to the extent possible, at home and stuff, with lab 3. But what I strictly mean by free fall, like even if I'm not, before I say anything about what's true under free fall, when I talk about free fall, what I strictly mean is an object influenced only by gravity. And what that really means to me is an object, like if I talk about a free fall, it could be a few minutes situation, it could be a few seconds situation, but a situation of free fall, an object that's in free fall is an object that is influenced by or forced by, if you like, pulled or pushed or interacting with planet Earth and nothing else. Like this ability that planet Earth seems to have to pull things toward it without even touching those things. This ability that we call gravity, right? But we are not claiming to know much about at this point. We're just claiming to observe this idea. It's a very, very old observation. People have observed for thousands of years that things tend to fall toward the surface of the Earth if you let them go. We call this phenomenon gravity. We do study this phenomenon in physics in a big way, but we're not claiming to yet. I'm not assuming that I understand anything of the details of gravity, like why this happens or how this happens. All I know is that for some reason, the center of the Earth seems to be able to pull things toward it without touching things. We call that non-contact pull gravity. And if an object, like a brick, or a string, or a can of soda, or a human being, if an object is under that influence, but only under that influence, like not sitting on a desk, if it's not riding down a hill or interacting with the friction of a ground, or not being pulled by a string, if an object is free falling, we mean to say that it's being pulled by gravity and by nothing else. Now, I have to make a big deal of that definition. So that's what free fall means. Free fall means under the influence only of gravity. But please understand that that doesn't necessarily mean that you're moving straight down. When you throw something up in the air, once you let it go, it's in free fall. The moment you let it go, we call that free fall. It could be on its way up. It could be or it could be going to the side. It could be going in a parabolic curve. Okay, so just to be clear, when we say free fall in physics, I could sort of do some fun, like if I just throw something up, the whole motion that I just, from the moment I released it to the moment it touches something like the ground or a wall or a string, from the moment I release it to the moment it touches anything else or encounters great wind resistance or something, the entire motion is called free fall. The upward part, the over part, the down part, all those parts are called free fall motion. So something doesn't have to be moving down to be free falling, okay? However, and here, I'm just going to turn the page, but you can stop me. I'm sorry. However, so any object that's in free fall could be velocitizing any old way. It could have a velocity pointing up, a velocity pointing down. The velocity could be any number, in fact. But a freely falling object okay, I want to say as clearly as I can, here's one example of the relationship between acceleration and velocity. Okay, something that is in free fall, it could have any velocity at any moment. It could have an upward pointing velocity, a downward pointing velocity, or even a zero velocity if it's in free fall. Like it could be going in some crazy arc, and we would call it free fall as long as nothing else is touching it. Nothing is touching it. But no matter what, if it's in free fall, why we're calling it free fall, even if we don't understand anything about gravity, the one thing we understand about gravity is things are like eventually landing on the ground. Things are being yanked to the ground somehow. That is, as they're coming down, they tend to be speeding up more and more and more. Like if you drop, like why do I believe they're speeding up? Because if I drop something, it starts from rest, but then it clearly gains speed because it's eventually moving. When things are dropping, they are speeding up. When they're going up, they're speeding down. I mean, they're slowing down when they go. And in either case, if you really think about negative signs or positive signs, no matter what is part of the definition of free fall is that an object in free fall is necessarily accelerating toward the ground. It is not necessarily moving toward the ground if it's in free fall, but it will eventually be moving toward ground because it necessarily has an acceleration that points down. Does that mean the acceleration is necessarily negative? Well, if down is designated to be negative, then yes. You can designate down as negative. Sometimes it's very convenient to designate it positive. So I can't actually say whether acceleration is necessarily negative or positive, but it is down. Now, lab 3. So this is just by definition, okay? I'm saying if something's in free fall, if we understand the concept of acceleration and we understand the concept of free fall, then something in free fall is definitely accelerating, and it's definitely accelerating in a downward direction, like no matter what. Now, is it definitely accelerating at any particular number or even at any particular rate? Like, how do I, like I'm saying something falling down is definitely accelerating. It's definitely changing its velocity. Could it also be changing its change in velocity? Like, could something falling down be going like 1 mile an hour, then 2 mile an hour, then 4 mile an hour, then 7 miles an hour, then 12 miles an hour? Like, could it be doing that? I don't know if you see what I'm doing with the numbers, but one could ask, when something's falling down, like we know it's gaining speed. We know it's gaining speed because it was at 0 when you held it in your hand, and you open your hand and the thing now has some speed. So when things fall, we know they gain speed. Do they gain in the speed? And I'm asking this rhetorically. I'm not actually asking the class, because what I want to make clear is the answer according to lab 3 is no. Like, the point of lab 3 is not a number. It's not to get, I mean, I know you get numbers and stuff, but the ultimate finding of lab 3 is not any particular number. It's just the finding that whatever rate at which things fall, that rate itself doesn't change. Now it turns, okay, and therefore all this physics applies. What is that number? Well, okay, let's actually choose a coordinate system to be clear here. Let's actually say, all right, like I want to deal with freely falling objects, but a freely falling object could go up for a while and then come down. So like I might have to deal with more than one direction. So let's choose a coordinate system. Let's choose a coordinate system. I'm going to choose to say up is positive, whatever anything moves in the upper direction, down is negative. Okay, I'm going to say, and I'm going to say according to lab 3, A is constant, and according to this coordinate system, according to my coordinate system, whatever the acceleration is due to free fall is negative, just according to this choice, coordinate system. And according to lab 3, whatever that negative number is won't change. Now, it does happen. You don't, I mean, depending on, depending on the semester and depending on the conditions, sometimes we do or do not directly do this in lab 3, but once we believe that acceleration is a constant. Oh, and by the way, when I say that lab 3 shows this, I don't want to get too into it because this isn't lab time, but what I mean by that is that if you do the strings correctly, assuming we did the string thing, the fact that a certain pattern of bolts will accomplish the task, that a certain spatial pattern of bolts will make the bolts land at equal time, but other patterns will not, is ultimately what shows that what's operating here is a second derivative, but not a third derivative or a fourth derivative. I mean, and I can talk to in more detail about that if people want, but if you get a string that works, what you've shown is that A equals A naught. Now, once you believe that, it's easy to plug backwards into the equations that we did Wednesday, and we'll do this, and just drop something and time it and find that near Earth, empirically, oh, sorry. If you just drop something and time it, what you find, it just empirically, in other words, there's no law that said this had to be true, and there's no law that says that the following is true on the moon or Jupiter or anywhere else in the universe. But on Earth, you drop something, it turns out it gains velocity at approximately a rate of 9.81 meters per second every second in the downward direction. Downward direction, I'm going to call negative now for now. And 9.8, I'm going to round immediately up to 10. If we're in the lab, we want to be as precise as we can, but no more precise. So in the lab, sometimes we want to be more precise and say something like 9.8 or even 9.81. But no matter what we say, even in a lab, we're chopping off digits. I promise that that number G in reality is like the number pi, like the digits go on forever without pattern or repeat. So somewhere you're chopping off the digits, and everybody in physics, when they're not inside a lab, decide since we're chopping off digits anyway, let's make our life easy and chop off to 10. And that's what we're going to do in this class. Empirically, the rate at which things accelerate in free fall is approximately constant. And that constant, which points constantly in a downward direction, is approximately 10, which is a nice, easy number to work with, which means that if we're about to do a new exercise right now, like if I'm about to make up a free fall example right now, or if there's a number in the homework, we're going to do the free fall example just like we did last Wednesday, only we're going to bear in mind now that there might be some implications of this negative sign. Like we're going to bear in mind that things can go up and down, and that might have some subtleties. So I'm going to start by saying this, like, and tell me, I'm going to turn the page, but tell me if that's too early if you want me to go back. But I'm saying, I'm sorry, one other thing. Whenever numbers are involved, if we're talking about the acceleration in free fall near the surface of the Earth, when numbers are involved, we use the number 9.8 or 10. Well, actually, let me just write this. I'm sorry, hold on. Okay. All I'm talking about right now is free fall, because free fall is the natural and very pervasive case. Free fall is the natural and pervasively occurring case of constant acceleration. And so what we're concerned in physics is the larger issues of constant acceleration. Free fall is an example that stares us in the face all the time and that we need. What I'm saying about free fall so far is that lab 3 matters, but is that whatever rate something does accelerate in free fall is a constant rate approximately. And approximately, it's not strictly true, but it's approximately true. But whatever that constant acceleration is, whatever that number is, we'll call lowercase g. G from now on in this class, or in the world of physics, lowercase g stands for the approximately constant rate of free fall acceleration, whatever the number is, okay, whatever the number is, and whether you call it positive or negative, and whether you measure it in feet or meters or miles or whatever, per second squared or whatever per squared, it's called g. That's why I put a triple equal sign there. But what g happens to be approximately near the surface of the earth in meters per second squared is around 10, in feet per second squared is around 32. The number is not the important thing. The number changes from planet to planet and from unit to unit. The number is not the important thing. It's the constancy of the important thing. Okay, so that's number one. But it does point, I shouldn't say negative. I should say it's down no matter what. So now, if that's true, here's the exercise I'm going to turn. I know I've built this up for like hours now. So I'm going to write an exercise very much like what we did on Wednesday, almost identical. Only this one's going to involve up and down. I mean that one involved like horizontal, like something speeding up at 5 meters per second squared. For the example today, it'll be 10 meters per second squared. That shouldn't change anything. But here we're allowing for the possibility that something could go in a certain direction and turn around and come back. Like I could throw something up and it could come down. In fact, that's what we're going to do right now. So here's. Okay, for today's exercise, here are the givens. Okay, and we're going to go into breakout rooms for good or for bad. You can't, this board doesn't go into the breakout rooms. So just the given is as simple as last time. Assume almost as simple as last time. Assume something has a constant acceleration, only this time we're saying an acceleration that points in the downward direction, which we're calling negative. So a downward acceleration of negative 10 meters per second squared. Now assume we throw something up, okay, up at positive 50 meters per second. Okay, those are the givens. And notice we don't throw it up at 0, then it wouldn't go anywhere. We throw it up at some positive velocity, positive instantaneous velocity of 50, What I'm going to ask now, I'm going to ask questions. I think they're simple to ask. I don't think they're necessarily easy to answer right off the bat, but they are all possible and fair to answer just from the equations we have. Like you shouldn't have to, from the concepts, from the English we have even, but you shouldn't have to introduce any new knowledge to answer a couple questions that I'm now going to write on the next page. So please bear with me. Like, well, I guess I can write these givens again, but so if again, the givens are, I'm sorry, and I see that people in the waiting room. I'm sorry, I just let someone, and I see there's things in the chat. I'm sorry, I'm getting ahead of it. I'll check the chat in a second. I apologize. I'm getting in my head. But let me just write this and then I'll check and we'll all catch up each other. How much time? Okay, now this is what I want to look at the chat. I want to, and I apologize in advance, and maybe part of the chat is that, okay, I'm going to look at the chat in a second. I'm going to put you in breakout rooms in a second to solve this problem. I want to just read the problem out loud again or try to clarify. And then I'm going to, go into see what's what in the breakout rooms. And just like last time, probably, because class ends in a half hour, probably by the time we get back together and I say some answers. I mean, I think that's going to be it for today's class. And hopefully this will again be like last time. Like hopefully there'll be some ahas or some progress forward on this. Also, and also the result of this is you'll see that some handy dandy new shortcut equations may pop out of what we're doing, but that will be the result. But you don't need any new ones to do what we're doing, not at all. You need to just follow the model of what we did last Wednesday. In order to solve this, I'm saying, given that we throw something up at this initial velocity of 15 meters per second, I want to know how far this thing has traveled in the first second, just like last time. In other words, where is it at t equals 1? And you can assume that it starts at x equals 0, if you like. How far has it traveled at the third second? Just another example of the same thing. But then I'm backing up just like last time and sort of reminding you that, in order to get those answers, they're harder than they look in a way. Each of those answers will take more than one step. One of the steps you need to think about is how fast is this thing going actually at every moment? Like before you think about how far it's gone, think about how fast it's going at any moment. So I'm just trying to force you into that there in question 3 and 4. At t equals 1, what is v? What is v instantaneous? Then at t equals 3, what's v instantaneous? Okay, again, please remember from last time, in order to solve these, you're going to have to think about average velocity, but I'm not asking you about average velocity. It's incumbent on you to use that as an interweaved step to get to the answers I'm asking for. Ultimately, what I'm asking you here is exactly what you'd think I would, I think. I'm saying, given these facts, if you throw something up in gravity, you throw it up at 50, how much time is it going to take before it reaches a peak height? Like it will reach a peak height, right? You throw something up, it'll eventually reach a peak height and start coming down. I actually want to know how much time will it take till it reaches the peak height? And then even better, how high is that height? Like, I do believe if I just say to you, how I throw something up at 50 meters per second in a gravity field, I do believe it's totally solvable to know, oh, well, then it'll go high. And that's what I want to know from all of you. Question 6 here on the side is how high? That's the ultimate point of this question. There's a million different ways you can get it, but somehow you have to go through some steps. Either, and they might not ultimately necessarily be mine, but I'm asking you today to go through mine. But there's one other thing. In order to get ultimately to how high, if you go through my steps, you may find at any moment it's much easier to put all this information together through a chart. You may be very tempted. I would highly suggest you might want to, in fact, I'm going to do something. It would be extremely useful. And again, I can turn back in a moment if anybody wants. What I would highly recommend is something that looks like this. It won't look exactly like this, but I would highly recommend making a chart like the one I've done here. And from such a chart, one could even make a graph. Most people at this stage hate graphs, and most people do graphs when they're told to, not because they actually help them understand anything. Eventually, graphs become very nice to actually, but I'm saying for the moment, what would be really helpful to work through this would be to make a chart. I guess I'm actually saying, please make a chart. When we come back together, we'll look at the results, and you'll find the results, the answers to the questions I'm asking. You'll find them somewhere in a chart if you make a complete chart that takes the object. Eventually, this object is going to go all the way up, and it's going to come back down to where it started from, and then the problem is over. The problem will take that many seconds. But I want answers to this. I am aware it's 105, and I want, my ultimate goal of this is for everybody to see how to do a thing like this and see other equations that pop out of it. I'm sorry. I'm going to check the chat first. I'm sorry. This. Oh, yes. Oh, okay. By the way, looking at the chat, yeah, I'm actually relieved to see. Okay, so there was some, and some of the chats are private and some not. But, so some people totally thought today was Tuesday. How could you think today was Tuesday? It was only Tuesday in the world, right? Some people are actually apologizing to me that they thought it was Tuesday, and that's why they were either late or whatever. And please, I'm like flattered and thrilled that you would even bother to apologize for me. I did not know it was Monday either until I was right about to had to teach the other section, and I couldn't. I totally did not understand it was Monday either. So no need to apologize to me. But yes, this is Physics 203. And again, if you could, I'm definitely posting this recording tonight, and nobody had this section today at 10:50 for that same reason. So please tell your friends if they're in the other section, like this is it for everybody. But anyway, yes, okay. But then assuming people can hear me and sort of know what's going on, what I'm getting at, again, the problem for today is this one right here on the board. There's no new equations yet. It will produce new equations, but you can solve this entirely with the 5 that we have so far, but really the last 3. It's really, the middle, the first 2 and the last one. Those 3 equations can solve all this, but you have to be careful. There are right answers and there are wrong answers. I'm going to ask everybody to do this problem that's right here on the board. It's questions 1 through 6. It will take us to the end of the period, I think. I'm going to gather us back just in time to give answers, for good or for bad. Can I just get a show of, so I guess this recording will be very boring, but can I get a show of hands that you know what I'm asking, and you, like, do people get what we're about to do? Like, even if you don't know the answer. I'm nervous. Wait, do people, oh yes, okay, great, thank you. I didn't expand the gallery view sufficiently to see that. Great, all right, so we're going to do breakout rooms now. I know they have mixed implications, but this is the problem. And in fact, also, I will say, no, I will say nothing. I'm going to start putting solutions while you're in the breakout rooms. I'm going to just start doing it out. So at worst, when we come back, if there's a little time, at least I will show you all what I did, even if we don't have a chance to share yours. But okay. Okay, so please go to your rooms. Okay, so Devin, can you hear me? Are you cool? Or Kaylee, Isadora? Okay, so great. And Isadora, can you hear me? Are you there? Isadora? Okay.
thing here. Professor?
Wait, hi, yes, sorry. Hello.
Sorry, I just
Hi.
wanted to see questions. What was question 5, 6, and 7? I thought I had copied it down, but I only got up to 5.
Oh, yeah, okay, sure. Sure, thanks. And I didn't even know this word. Yes, okay, so question 5 was how much time does it take until a peak height? I mean, how much time elapses until this thing gets as high as it ever will before it starts coming down? Does that make that's okay? That's question 5. And then question 6 is how high is that peak height? Like how high does this thing actually get before it starts falling down?
Cool. Okay.
Yeah, okay. And does that mean so you guys are trucking? I was actually about to visit you, but so you guys were good until that, like you're just moving along and then just didn't know those, and now we're going back to those last 2 questions.
Well, yeah, we've been like talking about it. Like, there's definitely like some disagreements with like how to go about each problem, but we're talking about it. We're making our way through, seeing what we agree on and don't agree on.
Actually, I'm thrilled to hear there's disagreement. Oh, that makes me want to bring everybody back in here. That's great that there's disagreement. All right, I won't interrupt anymore, but I know it sounds crazy, but if anybody ever says they disagree, that means they're on the right. I know that means you're doing something right, because you can't even disagree until you're specific enough. I mean, that means people have opinions, so they're doing so. That's great. I won't interrupt anymore.
Yeah, we're definitely like going like back and forth, like giving our reasonings and stuff and seeing how we follow through with it.
Awesome. All right, that's my ideal. Actually, okay, I'm glad to hear that. I'm going to cut you off. I want to hear some of this in the whole group. Okay, all right, thank you. Okay, yeah, okay. Hello. Okay. Okay, so you can hear me, yes, I think.
We can hear you.
Okay. So I have to now. I wish I wish class were longer because I just got a little taste from 1 or 2 rooms that I got a small gathering. I mean, a small sense. First of all, I know there wasn't enough time. I'm pretty sure I did not give you guys enough time. I'm only cutting it off because we are going to run out of time, and I'm too excited in a way because I gathered that there was maybe something approaching disagreement here or there in a couple of rooms. And I said to one person, and I really mean this, I like nothing better than disagreement in a physics class. In fact, we used to do this thing called board meetings all the time. They were all about organized debates in physics class that I'd like, and I think you'll still be doing in lab to some extent. And I'd like to do more of them. They're harder. We have to reorganize them for Zoom purposes and stuff. But I mean, I learned nothing is a more a good way to do physics than to have disagreements, really. And for a lot of people, that's shocking because it's science and all of that. But no. When in other classes, it may, what am I trying to say? You totally can disagree all the time in science. Of course, you can sometimes find out that you were wrong when you were disagreeing, but you weren't wrong to disagree. If 2 people are actually disagreeing about how to do something along these lines, I actually really wish I were a fly on the wall, or wish I could get everybody to engage in these disagreements for longer before I resolve them, because you just can't eat, because it's resolving these disagreements that actually makes everybody own the equations rather than just accept them. So part of me really wants to hear about exactly what the disagreements were right here. And I'm going to try to get this, but also because time is limited. Let me make, I haven't written down any answers, but I've written the beginnings of my chart. And I do think the chart can be very illuminating for people. Even just making the chart, like regardless of what answers you put in it. I want to make clear that if you make a chart, sort of like what I was doing before, a chart can sometimes even reconcile these disagreements. Just note that this is what I mean by the columns. In the first column, you put any given moment in time. That's obviously measured in seconds. Okay, then in the second column, I'm talking about instantaneous velocity, v without a bar over it. So it's measured at whatever it is at meters per second. And by this column, I mean, what is the instantaneous velocity at the corresponding time from the left-hand column. So like what's a given for this problem is that plus 50 that I wrote in there next to the 1. Like to start off the chart, what we know in this problem is that at time, I'm sorry, not at 1, at 0, I'm sorry, at time equals 0. Yikes, that was a weird thing for me to do actually. But right at the beginning of the problem, we're told that this object is thrust upward at 50 meters per second. So the value of v at t equals 0 is plus 50. Then by v with a bar over it, what I mean is average velocity, but I didn't fill that in yet because that may be where people are disagreeing or something. I need to make it clear that average velocity always is the average velocity between 2 moments in time. And some of you might interpret my column different ways. When I say average velocity, do I mean the average between t equals 0 and wherever you are in the column, or do I mean the average between the very last 2 numbers in the column? There's more than one right way to do this column, more than one right way to do it. So, I don't want to tell you what, but you have to know what you're doing. You have to make a decision. When I say average, like when you're calculating average velocity, between when and when. You'll see that in a minute when we do it together. And same thing with x. X is displacement measured in meters, like how far the thing has gone. But that means since a given moment, we can establish that at moment 0, this thing has gone nowhere. So I filled in that 0. We know that. But then if I ask, if you're filling in this column and someone asks like, how far has it gone by t equals 2? You have to actually consciously recognize what you put in that column. Are you putting in how far it went in total since the beginning of the whole thing? Or are you putting in how far it went in the very previous second? Like that's a decision. Either one will work as long as you're consistent. And I'll hear that from people in the remaining minutes we have. But then finally, one thing I'm going to say off the bat is, one thing you definitely know for these columns, no matter what you do, what's a given here is that -10 is the acceleration all throughout for all time, no matter what. Whether this thing is moving up, coming down, sitting still, the one thing that you know is every entry in your last hand column is -10. Like that actually is the fact of gravity. And now saying that, I guess what I just want to say is like, let's just, well, yeah, let's go to the actual questions, which is a matter of filling in the column. Like my very first, so I'll turn back to this. I'm going to fill in the answers to the questions I asked into those columns. But the very first question I asked, I believe, question 1 was at t equals 1, how far has it gotten? I mean, tell me if I'm wrong, but like, so at t equals 1, how far has it gotten? So that's the first, I think that was my first question. And whatever answer I get, I'm going to put into this chart. And maybe some of you put in other things before you even got this. But I'm turning to the class now. I know there's like 7 minutes, but anybody from any room, especially maybe one of the rooms that told me there was debate, does anybody have a thought that they want to share for this first question? In other words, what we're ultimately looking for is this, the answer that's going to go in here. But does anybody have any thoughts of how to get it? Or do you want to just say an answer and I'll tell you if it's right or wrong, or up to you? But anybody? This is either why breakout rooms are good or bad. So I'm asking, does anybody have, I know there's 4 minutes now. All right, should I just put in the answer that I think it is, and you'll see if you, okay, I'm afraid to do it. Does anybody want to have a thought of what they think? Am I right about question 1 is how far has this thing gone in the first second, right? Wait, can I get, or have I lost? Can you hear me? Oh wait, can you guys hear me?
Yes, we can hear
you. Okay,
you.
sorry. Okay. Okay, all right, fair enough. It's we're all going to spend the rest of our lives wondering whether it's more embarrassing to be me or to be you in those situations. But I think me. All right, so I'm going to say the answer. Thank you for someone had guts. Oh, I totally appreciate it. Now look, I got to say, I'm seeing answers in the chat. That makes me so happy. I'm seeing answers show up in the chat. I have to say right now, I'm going to look at those answers. I'm not looking at names. I don't even know if those answers are private or not, but I'm telling you, there's no reason that they should be private. You should be proud of yourself for putting any freaking thing into the chat or into my life right now. And I love the fact that both of the numbers in the chat are both not private. Thank you. That is like so A-worthy to me. It's better than a video. And they're both different, which means no matter what I say, put it this way. I don't care if the one person's right and the other's wrong. If you put a number in that chat and now you're about to find out what the right answer is, the fact that there's disagreement at all means we're getting our tuition worth when I give you the answer, right? It means that there was like a reason to bother up to show up to this class. So like everybody's a winner. Since there was 2 numbers given to me and they're different and only one of them could be right, I commend both of you. I'm going to tell you right now, yeah, I think the answer is 45. Okay, I do think the answer is 45. I totally see where the 40 came from. I think the 40 is on the right road to the 45, but the answer is the 45. And I know we're running out of time, so I'm gonna, well, Elizabeth, could you say why? I totally get why the 40 is a thing to say. I think, but then go another step to get, Elizabeth, can you explain where you got 45 from? Or am I now punishing, is that a punishment for having had the guts to put it in the chat? I don't know. Actually, I take it back. I didn't want to,
okay.
No,
go. I was basically following from the last problem you did. It's basically the same problem. So you follow the same steps.
Yes, that is totally true and good, right? But for everybody, I know like all this takes a couple times of doing for everybody. So yeah, if it didn't seem, so she's not saying, but yes, that's right. So I think to be the fast, I'm gonna, in other words, well, here, I'll do it. And I know I'm gonna do this one quick one, then I'm gonna fill in the numbers in the chart so people could see the end result of all this. And then we're gonna go, of course, but hopefully, and we'll pick up from here Wednesday, but whoop, sorry. The key point in English, I'm about to write it in equations and hope, again, the goal is to see how the equations are saying the English and vice versa. But in English, what we said last time, what Elizabeth is saying this time is, look, this thing started at a rate of 50. It started at 50, but the rule is it's losing 10 always. Like it starts at positive 50, but the acceleration is negative 10 meters per second squared. That means, that rule, that last column means every second this thing subtracts a total of 10 meters per second of its velocity. Subtracts because of that negative sign, because it's moving up while acceleration points down. So in the first second, just in English, it goes from 50 to 40 meters per second. That is, I'm saying, if you want to think of it equation-wise, what I'm really doing, she's saying, well, the definition of acceleration is change in velocity per time. if you want to see, we know the initial velocity, oops, sorry, I'm not going to press it, is change in velocity per time. If you're looking for the velocity at t equals 1, I'm rearranging that equation, you would say v equals at plus v naught. In other words, the velocity at t equals 1 is we're really just saying, oh yeah, what's the velocity a second later? Well, it started at 50, it's losing 10 every second, so it ends up with 40. That's literally what the equations are saying and what the logic says, I think. But that means, now that's the 40. So a lot of people would write 40, and 40 is a thing. Like 40 is the next number in the V column. I mean, 40 is very important information. It's just that what the 40 is it goes right here. That's the 40. That's the velocity that this object has attained at the moment the clock strikes 1. What that means is that on average between those two, the average for that 1 full second, like as it's slowing down progressively from 50 to 40, on average it goes 45. So equation wise, what we're really saying now is its average velocity from the beginning of that second to the end is the average of velocities because the acceleration is constant. So the velocity really went from 50 to 40, like I'm literally averaging those two numbers, which I'm allowed to do here. And we get 45, and then that, so I would put 45 in that column. Now then, technically speaking, we have one more step, and it's distance equals rate times time. What does that really mean? Distance equal really is average velocity is defined to be displacement per time. So the displacement you travel in some amount of time is the average velocity times that time that we started at position 0. So how far do we get in 1 second if we're traveling 45 meters per second? For that 1 second, we traveled 45 meters in that 1 second. Like that. So 40 is a key number. I'm glad someone said it. I'm very glad Erica said it. But then you that 40 is your instantaneous, your final velocity at the end of 1 second. So on average for that second, you've got 45. Now I know we're just about done, or seconds, but what that then to go, and so I really did use all 3 equations. If you're thinking of it equation wise, you really actually have to use all 3. It doesn't mean you have to use any. Like if you get the logic and you can see it in your head without writing down equations, then you can do that too. But if you're thinking equations, it is all 3. Ultimately, then what we're saying is, and someone wants, whoa. What? Hold on one sec. Hold on. One sec. So just to fill, I know we're just like done, but to fill out the chart, then I'm saying this thing. Look, not coincidentally, yes, the one every moment, every second, this thing loses 10 meters per second of velocity. So by this pattern, it's going to take 5 seconds until this thing is fully out of velocity. Like it will have 0 velocity in 5 seconds. That's when it'll stop moving. And in the very next moment, in the very next second at t equals 6, it'll go to negative 10 meters per second velocity, i.e. start coming down. Okay, that's like the next page if we have time. But there's no contradiction here. So, so the answer to question 5 is 5 seconds. It'll take 5 seconds to reach a peak height. And if I want to know how high that peak is, I can fill out all the rest of the numbers on this chart. I can fill out the rest of the numbers on this chart as long as I'm careful and know what I'm doing. Like if average velocity means average of the, wherever you are in the column with the beginning, like if right here by average velocity right here is the average from t equals 0 all the way to the end t equals 5, the average velocity for the whole thing, and we're just about done. The average velocity will be 25, right? It started off at 50. It slowed all the way down to 0. So its average is 25 there. And if it did on average 25 meters per second of velocity for 5 seconds, then its total will be, I just skipped to the end. There's other numbers to fill in the column, but any row of this column I can do by this method is what I'm saying. So how far did this thing get? Like, answer to question 6 is 125 meters. If I throw something up at 50 meters per second, it will go up 125 meters before it starts coming down again. I can even show that by finishing all the numbers in the column, which I will right now, I guess. Right, and then, I did that I did this column fast, but I just did it the same, I just iterated the same process that we just said, but just notice the numbers there, and we're gonna stop right here. Just notice those numbers there, they don't look like a pattern at all. They look weird, like they look like our pattern is gone. Our pattern is in the velocity column, or our obvious pattern, but there really is a pattern even all the way through the end. Like in the very first second, you go up 45 meters because you're going really fast. You're going 45 meters per second. But then at the end of 2 seconds, on average, you've been going 40 meters per second, like on average for those 2 seconds. But you did it for 2 seconds. That's where I got the 80 from. But look, you're slowing down. Like in the first second, you actually traveled 45 meters. In the next second, if you subtract in your head, if you look at the 45 and 80, you've only gone 35 meters. Then in the next second, you've only gone 25 meters, then 15, then 5. Again, I'm saying this, but just notice what looks like a jumble of numbers that you could never, like where did I come up with those numbers? Who would know that? The numbers actually do follow the pattern of every second this thing is traveling 10 meters less than it did in the second before, because it's traveling 10 meters per second slower. And these numbers will then continue on the other side for the next 5 seconds. This thing will come down with the exact same pattern of numbers flipped on its head. And I've gone over time. And I've actually really gone over time. I'm sorry. So I'm totally going to end there. And I thank you very much. I didn't realize it was that late. I'm leaving right now. Thank you very much for being so indulgent, all of you. Bye.